Hi, in this video I will discuss peculiarities of a ternary plot. Sometimes it is called ternary graph or triangular plot. Not the same as simplex or Gibbs triangle, these are different things. If you ask Google for triangular or ternary plot, you will get surprisingly uniform answer. But it is certainly a puzzle. We are all used to 2D plots or 3D plots where any point on the plot can be easily projected to the coordinates. But if you put a point in this plot, how to read it? And if you never met this plot before, you might think, is it something old or out of my field? I must say, yes, it is rare, but it's not out of my field for sure. I met it first in 2007 reading this paper where people discuss the differentiation of hematopoietic stem cells and defined them by the placement in this triangular plot. And if you think 2007 is a long time ago, you can inquire Science Direct and see that even up to 2026, 5 and down the list of 166,000 publications, this plot is still in use and likely will be used in the future. So after you accept that it is relevant for the science today, you still have a question. If I place a dot inside this plot, how do I read it? And of course you can read it by projection perpendicular to the one of the three coordinates, or you can draw a line through the dot from the corner to the opposite scale, or it might be a grid and you follow the grid. You can read some details in the Wikipedia and find out that all of those possibilities exist. Never mind this empty triangle. And to be more to the point, let's have a look at our package Ternary. And if you call ternary plot in this ternary package, it will nicely draw you this triangle with the grids, with the coordinates head to tail connected to each other. And if you place a dot over here, it is certainly a lot on this coordinate and a little on this. To be more precise, for every dot you read it in the following way, that you follow the grid to the left, read the value on this scale, then upright go to the second scale and downright to the third one. And if you are doing it correctly, the sum of those values is always 100%. Which also means that this is a plot of the percentages or fractions, not the absolute values in your data. Let's see how it will work in R. For the data, I will use rainbow colors. You can define yourself how many colors you want. I would take 12 for a starter. First I call it and then they come in a hexadecimal format. Then I make a data frame of RGB channels, rename column names, and I create this table of 12 colors with the red, green, blue channels and intensity in each. So the first color is obviously red, the fifth is a green, and the ninth is a blue. The advantage of using colors is that you can position them in a three coordinates environment, but also you can ask for color and see literally where it is on your plot. So we call ternary, we reduce margins a little, and then we can call ternary plot, but immediately reduce the font size. And in this case you will have this nice empty plot, perfectly triangular, with all the scales from 0 to 100, 0 to 100, 0 to 100, and the grid, of course. For our data, we better annotate the corners and the scales, and then we will call ternary points from my colorful table, and here we are. What is peculiar in rainbow colors is that it's always two channels, not three of them, and therefore they always lean to the sides. There is nothing inside of this triangle. On this plot you can see how channel intensities are changing. When you start with the red, it stays 100, but then green is increasing, then the green stays 100 and the red disappears, and the blue is increasing, and then it goes back to red. It's always two channels in a time. The distances are a bit of a puzzle. Are they really equal between dots or not equal? And you can also change the data set from 12 to 24, and you will see that it's still the same circular pattern, only the questions of distances between individuals persist. Of course, this plot does not measure distances between dots. It simply reads channel intensities and places all those dots according to the channel values. That's all what it does. Distances are measured in dimensionality reduction plots. If you want something inside, you can call named colors reserved in R for general purposes. Call them distinct. What will come first is this long list of 502 colors with numbers at the end. I don't want it. I want only basic names, and then convert to RGB and then call it. This will reduce the list to 128 colors with the names and with the channels values. Good. We can replot it on an empty plot or add it to here. Let's add it. And because they are named, we can add the text. So you can see all the names and positions of the colors. So this is the mostly red area because red channel is high and green and blue are low, and so it happens for the green corner and the blue corner. Looks pretty good. And now let's check our knowledge with a single dot. Let's select one color and then make a new empty plot. Then get RGB channels as a fraction. So we see that for red it is 0.6 somewhere here. Then for green is almost nothing somewhere here. And for blue is 34, is over here. So the dot should appear around this place. Let's check where it comes. Exactly where we expected. Let's go back to the case of 12 colors and try to plot them in a 3D coordinates. So we define red, green, blue colors as x, y, z coordinates and then ask for a scatter plot, and then we have this. Similar to ternary plot, we place our dots according to the RGB values, but the resulting pattern is pretty complicated, And if we follow the dots how there are in our series, first we move along a green scale, then red, then blue, then green again, then red again, then blue. So this is a pretty complicated trajectory, much more complicated than we have it in a ternary plot. And one more option would be dimensionality reduction. So we have a 3D, we can convert it to 2D using PCA. Similar to the scatter plot 3D input, I will use the transposed data of my 12 colors, where channels are in the columns and color names are in the rows. For this we can take those libraries and then use a transposed 12 colors, then plot the whole thing. Unlike to ternary plot or 3D plot, coordinates here are created during the calculation of differences between individual data points, and they are placed relatively to one another in some abstract scales, demonstrating you how different, how similar they are. That's the essence of the dimensionality reduction. And of course you don't see the RGB channels directly over here. You have to combine them with the PCA biplot like this. So the RGB colors still present and give you directions where the red is prevalent, green or blue. But I had a difficulty to color those dots individually. With this package, this can be done in a limo with a plot MDS, where you have all those nice colors, but in this style. PCA trick works, and the picture is pretty simple as well. What can we learn from this exercise? First of all, ternary plot is not that difficult to read or to make. Secondly, sometimes it is more easy to read and to have impression of the data compared to 3D plot, although I can imagine that for some other data 3D is better than ternary. Curiously, dimensionality reduction plot can reduce your scales to a 2D and reproduce the simplicity of the pattern, at least for a case of the color sets. And color sets, by the way, is useful data set to test some ideas, because it gives you a position of the dots and the color of the dots at the same time. That's it, and thank you, and see you next time.